Welcome. Today we're going to talk about mathematical patterns. Specifically, we're going to talk about a little bit of vocabulary, two types of formulas that can help you when using mathematical patterns, and finally we're going to make a statement about credit cards, I think, if we can get to it. Now, let's start out with quick vocabulary. When I'm talking about a sequence, I'm just talking about a list of numbers. Any list of numbers is fine. Terms of a sequence would be an individual component of a sequence. Would help if I'd put a little of that there. Now let's make a sequence, a really simple one. I'm not going to try super hard to pull this off and to make this amazing sequence. I'm really going to be super lame here and say 2, 4, 6, 8 would be my sequence. Now, in my sequence, my term would be specifically any one of the numbers. 4 is a term of the sequence, 6 is a term of the sequence, so on and so forth. Now, we can use the notation for sequences to help us identify specific points about it. The first that they often like to use, or that I like to use, and that everybody should probably use with sequences, is the letter n. The letter n refers to the number of the term in sequence. So the matching n's for these would be 1, 2, 3, and 4. N of 4 means it's the fourth term in this sequence. If you wanted to be even more specific, you would use things like the ace of n notation, where like the second group would be a of 2. It's just telling you that not only is 4 in a sequence, it's also the second term in that sequence. In terms of expanding out the idea of ace of n, sometimes you need to make a generic formula in order to find out what higher terms are, so you don't have to write out a million terms. Like if you want to know the 400th term of this sequence, well, you could probably do it. The relationship's not that hard, but when you get to a more complicated one, you don't want to write out 400 terms. You want to use a generic term, and that generic term is referred to as the ace of n term. In other cases, I have to base my formula, or it's easier and more functional to base my formula off of the term in front of the term I'm looking for. So say I wanted to know what the 50th term is. In some cases, knowing the 49th term can get me to the 50th term easier than just not knowing anything about it. So I may need to know the ace of n minus 1 or the ace of n plus 1, which is to say this is kind of like my focus of direction. It's my orientation point, but I may look at the term after it in the sequence or before it, just depending on how I write my formulas. From here, we're going to talk about two of the formulas. The first is an explicit formula. An explicit formula, and we'll do one for the 2, 4, 6, 8 sequence. And by the way, my 2, 4, 6, 8 sequence I'm going to put vertically, because I want to put the n values over here. I just think visually it works better if I do it that way. So we're going to make an explicit formula for this. And what we're looking for is to see if there's some relationship between the first set of numbers and the second set of numbers. So is there something I can do to get from 1 to 2, or 2 to 4, or 3 to 6, or 4 to 8? Now my suggestion in many cases, and I've talked about this in a different one when I did a quick review of patterns, is to see if there's any difference, changes or common difference in terms of the numbers. So I would do 2 times 4, or 2 plus 2, 4 plus 2, 6 plus 2. So really the relationship is that it's going up by 2 every time. The nice thing about this pattern in that it's a sequence is you don't have to worry about the change in your n value, because it's always going up by 1. So you have the change component that you need. And if you'd seen that video, I talk about it in terms of equations a lot. So I would know that since these numbers are all the same, it's probably what I would have called then an x term. So I would do 2 times my x value and get this. So in this case, I would just say it's 2 times the number of the term. So if I know the term number is 3, I do 3 times 2, and it gives me 6. So that's my ace of n relationship, and that's my explicit formula, as it were. Now, the nice thing about this relationship is it goes up the same every time. Incidentally enough, just as an aside in a way, if I were to do this sequence, if I look at the common differences, and you might already see the pattern, if I find the common differences, it's 3, then 6, oh sorry, 5, I don't know what I was thinking was 6, and then 7. In the first group out, there's no relationship. So it's probably not going to be a standard in relationship in most cases. I mean, you could work one out, but it'll have other components to it if you simplify the formula. But look, 2 and 2. If you're in the second group, just as a where would you start even looking, you might start looking for n squared relationships. Is there some relationship between squaring the term? If it went out 3, you may look to the third power. If it gets gigantic, you may have n as your exponent. So it's possible that you'd have sort of a 5 to the nth power relationship. That can also exist. But at least if you have nowhere else to go, if you expand out those different into different columns, you can get somewhere that might help you get to where you need to be. Now, in terms of how we're going to use how you may see explicit formula questions worded, they may say if you have a sub n equals 5n plus 2. They may want to know the first 3 terms or the first 4 terms in the sequence. All you're going to do is pick your n values, and I want to know the first 4. So the first term I would just plug in. So for a sub 1, 2, 3, and 4, I'm just going to plug the number of the term in and then simplify the result. So in the first one, 5 times 1 is 5, plus 2 is 7. 5 times 2 plus 2 will give me 12. 5 times 3 plus 2 gives me 17, and 5 times 4 plus 2 gives me 22. So I can say that my next terms in sequence are 7, 12, 17, and 22. So if they give you the formula, they're making your life extremely easy for you, so just be happy about it. And that's where I would go with it. Now, sometimes you don't get a nice explicit formula. Not exclusive, explicit. Explicit formula. You get the recursive formula. A recursive formula is a formula where you base information off a term that you already know, or really the term before the term that you're working on. So let me make a little chart set up here for my beautiful pyramids. I know you were like, man, he should quit his job and get a job making pyramids. Well, I have other responsibilities, so I can't. So in my first one, these are my n values, by the way. I wanted to change from that blue because blue on blue is a little complicated. I have one little square. In the next one, I have, in my second term, I have 3. In my fourth term, I have 6. In my fifth term, I have 10. I don't know why I skipped over those. Sorry, 3, 4 is 10. Sheesh. 5 is 15. It's been a long day. So that's my relationship. Now, I don't see an obvious, okay, go from here to here relationship in terms of a explicit formula. I'll show you 2 ways to make an explicit formula out of this, but the thing that we want here is maybe to make a recursive formula. Like, is there any relationship in terms of how the numbers change using the term before it? So let's look at the little setup here as far as the differences. So 1 and 3, there's a 2 difference. Here there's a 3 difference. Here there's a 4, and here there's a 5. You'll notice that they're not the same, but you get a nice little look at them going up each time. So this is probably going to be some sort of recursive formula just because it goes up smoothly like that. And what we're going to do is base it off of the term before. So I'm going to pick 3 as my starting off point because it's always good to pick a number that you barely wrote legibly as your starting point and see is there some relationship between the amount that it changes and the term itself. So, or the term before, I'm sorry. 3 plus 3 gives me 6. That's interesting. Well, 4 plus 6 gives me 10, and then 5 plus 10 gives me 15. So the relationship is that if I add the term number itself, so say I start out with n here, and then I add the value of the term before it, so that would be a sub n minus 1, I can find any term that I want. So that makes a recursive formula because I'm basing it off a term that I already am aware of the value. It's not as helpful, of course, if you need to know what something is in the 38th term because you'd have to have you'd have to have at least the 37th to know where to go with it, but at least it's something to start out with. So this is a recursive formula because I'm basing it off the previous term in sequence, and it works. I showed that it did. But now it's time to look at the values in terms of an explicit formula. So I'm going to reset up the table really quickly. So 1, 2, 3, 4, and 5, 15, 10, 6, 3, and 1. Now, I'm going to make an explicit formula out of it. And I've seen it done two ways. I did it one way, and then I found a book, Prentice Hall printed or something, and they did it a completely different way. And it was pretty smart what they did. So let's talk about what they did, and then we could talk about what I did. So what they did is look at the idea of expanding out the values themselves. So they looked at these almost like they did a numeric representation of the visual relationship in the pyramid. So this would be 1. This would be 1 plus 2. So as you can see, the 2's match. This is 1 plus 2 plus 3. 1 plus 2 plus 3 plus 4. And then 1 plus 2 plus 3 plus 4 plus 5. So what they found out is really you're just adding all the values below it together and the value of the term. So they wanted to make a comparison statement about what if I looked at this sequence from the front end, and what if I looked at it from the back? And then I combine the two results that I get, and that should help me find some idea of what it's almost like they're taking an average of looking at it both ways. So they have the first ace of n, and they're looking at it from the bottom up. So the first term would be 1, and then it would go to 2, and then it would go to 3, and then it would just go up for a while. And then eventually you'd end up with your n value. The terms in front of those values would be n minus 1. So if n is 6, this will be 5. And then n minus 2. And then they thought, well, let's look at it from the other direction. I'm going to start out with n. And then I have 1 less than n. And then I need to add 2 less than n. And then dot, dot, dot. And then I end up with plus 3 plus 2 plus 1. So they wanted to combine those two things together to see if there's an averaging out of everything, if it balances. So they added them together. And when they did that, they got 2 of them, of course, because they're going to have to divide by 2. It's an average. So they looked at each one of these, n plus 1. And then they looked at 2 plus n minus 1. Well, 2 minus 1 is 1. And 3 plus n minus 2, well, 3 minus 2 is 1. And they found out, incidentally enough, that the next few were n plus 1 as well. Now, that led to the idea that really the pattern is n plus 1 times whatever number you have in the sequence. So if you have 37, then 37 would go right here. But we don't know how many, so we're going to say it's n. And then because they're thorough, they divided everything by 2 because they only want one sequence answer. And they came up with, they took 1 in, so it would be 1/2 n times n plus 1. That's pretty smart, I thought. So that's the way that they went about getting that answer. That is not the way that I got that answer, but it was a pretty brilliant way for them to organize it. So if you have nothing else, at least you can look at, if you expand it out, does it have that relationship? The way that I did it was sort of using the logic I explained earlier. So I've got the setup again. Except I looked at it as a geometric relationship in terms of I multiplied instead of looking at just seeing if there's common differences there, which of course we know there's not. But I started looking about, well, what if I multiplied the first number by something? So I multiplied the first number. 1 times 1 is 1. 2 times 1.5 is 3. 3 times 2, 4 times 2.5, and 5 times 3. And I noticed that those differences were always a half. What that meant to me, and it may have meant nothing to you, is I have one group out and the second group out. See, I found the differences in the first setting and then in the second setting, which to me meant, well, it's probably something with somehow n squareds involved. And I would imagine it's probably, since the half is the difference, well, what if I threw half in front? And is there some adjustment that I can make to get where I want to be? And so I did it. I plugged in 3, and I did 3, sorry. 3 squared is, of course, 9, and if you divide that by 2, you get 4.5, which doesn't get me to the 6 that I'm looking for. But then I thought, well, what's half of 3? Well, 3 divided by 2 is equal to 1.5, and 1.5 plus 4.5 is 6. So I adjusted my formula a little bit to say 1/2 n squared plus 1/2 n. And I thought about that for a minute, and I was like, okay, that's something. So I tried it for 4. So I did 1/2 of 4 squared, which is 16, of course, and then I did 1/2 of 4. 4 squared is 16, so half of that would be 8, and half of 4 would be 2, and 8 plus 4 is 10. So my formula worked. I just factored out the information. They both share 1/2 n, so I'm left with n plus 1, which I think is the exact same formula that they got. So that's how I did it, because I tend to work in that fashion. But either way that you do it is fine. It's just I was just showing you how I got it, so maybe you could. That's how you work. I don't know. Finally, let's talk about credit card evil for just a second. When I say credit card evil here, my goal is to get you to understand the idea that you owe a bunch of money if you don't pay it off. So in this case, the setup with your credit card is you pay 1.5% on your unpaid balance every single month, and then you get a $45 fee every month you don't make your minimum payment. So let's say you get some tough times, and how much will you owe if you started with a balance of $1,000 and you fail to make a payment for 5 months, which could be a big problem. Now, what I'm first going to do is make a recursive formula. The reason I need to make a recursive formula is because the amount that I owe is based on how much I had in my account before I started. So I have to know the previous month balance or before I can tell you what I owe right now. It's just the nature of the beast. So from here, I'm going to say that 1.5% is related, so I need to convert 1.5% into a decimal, and it gives me 0.015. I need to connect that with the value of my previous month, but I also need to consider that that balance exists. So the balance value of that would be 1 a sub n, or a sub n minus 1. So this would be the month before my previous balance. So I'm going to combine the 1 and the 0.05 to give myself 1.015 times a sub n minus 1, that's however much I owed, plus $45 for every single month that I don't pay, which is not very that's not very unrealistic. And of course, I should say that the n value has to be greater than 1 because there's no 0 months. It's a very generic recursive formula. So what I'm going to do is take my calculator and figure out how many I would owe after 5 months. In order to do this, you have to change the mode a little bit because you're going to use the answer value that you get. And you need to go over to where it says float, click over twice, and change it to 2. The reason that you want to do that is just to give yourself the ability to use the answer as a multiplicative term and actually put the 1.015 in front. If not, it just automatically adjusts it so it doesn't work properly. So what I'm going to do is, now that that's good, I'm going to quit out of that mode. So from here, my initial amount of money that I owe is $1,000. So I'm going to do $1,000, and I'm going to multiply that by, or I need to convert it into the mode form, so hit enter. From here, I can take that number and do 1.015, go into second, down to answer, and then it uses the 1,000 really, and then I can add 45 to it. That's how much I owe after the first month, second month, third month, fourth month, fifth month. So after 5 months of not paying my $1,000 bill off, I currently owe $1,309, and I think it was 45 cents. I'm going to bring up the calculator thing one more time to make sure that I'm right, and then I'm going to be done. So 14 cents, sorry.